Hi, and welcome back to Bayesian Model Updating in OpenCossan. In this tutorial, we'll look at a simple calibration example using Bayesian Model Updating. So I just have MATLAB open here with OpenCossan. And for this example, it requires the development version of OpenCossan, which you can get from GitHub. If you're using Mac or Linux, you can do this. You can download the development version using the terminal. If you're using Windows, you'd have to download Git to do so. So then you can just go to the directory where you have OpenCossan downloaded. So it's Cossan Git OpenCossan, and you can change to the development version, specifically the model updating branch of OpenCossan as follows with git checkout model updating. Press enter. So when pressing enter, this will have changed to the model updating branch of OpenCossan. Since I'm already on the model updating branch, it just nothing changes. So in MATLAB, I'm now in the OpenCossan head directory. So as with the stable version, I'm going to add all of the OpenCossan files to path. And then by going to docs, tutorials, and then this here, to degree of freedom model updating. And in here, there's going to be a file called tutorial Bayesian model updating. And this is the one we're going to open. So in this tutorial, we're basically going to generate some synthetic data of a model. We're going to do this by evaluating a model at a fixed point in its input space and then perturbing that, basically the evaluation by some random noise, basically creating some calibration data. Then we're going to use that calibration data to basically calibrate for the model inputs. So this is the development version of OpenCossan, and things are a little different with respect to the stable version. For example, to start using OpenCossan, I no longer have to call OpenCossan. I no longer have to initialize it. Instead, I can start working with OpenCossan directly. For example, if I want to create a parameter, I can do so like this, just by evaluating the code. So in this first section, we're just going to basically create the inputs to our model. So K1 and K2 are basically it's going to be two parameters at 1, 1. Then we're going to add some random noise to their output. So these are going to be two random normal variables with mean 0 and some standard deviation. We're going to then put those random variables in a random variable set, and then put them, all of those inputs basically into an input object. We're then going to create a model. The model is going to take in all three of these inputs, so all four, sorry, these K1, K2, and the two noise components, and then it's going to have two outputs, Y1, Y2. I just want to show you what this model looks like. So inside this folder here, you're going to see MATLAB models, and this one here calls eigenvalue perturbs. So I'm just going to open that file, sit here. What eigenvalue perturbs basically does is it takes basically all the inputs and creates a matrix with the K1 values, and then takes their eigenvalues and puts them to Y. And then for the outputs, Y1, Y2, we're just going to add basically the noise component to the output. And then we're basically going to, yes, that's going to go into an evaluator as it does with the as a stable version, then into a model, and then we're going to basically generate the synthetic data with Monte Carlo simulations. So we're going to create the Monte Carlo object, and then apply basically simulation. And I just want to show you what it looks like when we're running the simulation. So I'm just going to put a breakpoint in eigenvalues perturb, and I'm going to run the Monte Carlo simulation, and it should stop here. Yes. So basically, what this file is, this is basically your model file, and it takes in an input. It takes in tables and it outputs tables as well. The table input is basically going to be 500 times 4 inputs times 500 samples. So in the Monte Carlo, basically, when we instantiated the Monte Carlo simulation, we gave it 500 samples. So the input to the model is basically going to be 500 times 4. Just to show you what that looks like, I think if we do, yes, K1, we can see all the K1 values. It's just 1, 1, 1, 1, because we set that as a parameter. And it's going to be the P1s and P2s, which are going to be basically random. Okay. So then, yes, if I just step through this, it basically creates a Y value for every single element of that matrix. So if I just come to here, right, this is going to be a bunch of, yes, it's basically just the evaluations of the output at those single points, and then we perturb it by some data, by some random noise. So this is the unperturbed model evaluations, and here is the perturbed version of the first output. Okay, just going to set a breakpoint here after coming out of the Monte Carlo simulation. Right. So that basically stores the synthetic data in this object, synthetic data, synthetic data, which we're going to use for calibration. The next part is basically just a deterministic analysis, where we just run the model for our fixed input, just to get what the output should be if everything was deterministic. So then, let's see, it's these two values here, the two values that were quoted in the last presentation. Okay. Now we're ready to get to the calibrating. So if you remember from the last presentation, there are a couple of elements we need for performing Bayesian model updating. So we need a prior, which is going to be random variables, which sort of represent our initial guess or our initial knowledge about the variables. So in OpenCossan, this prior is going to be set as random variables. So in this case here, K1 and K2 are going to be uniform between some bounds, right? So if we don't have any information about our parameters prior to doing updating, we often model this information as a uniform distribution with just some bounds here. Just note that our real variable should be somewhere contained in our bounds. So the initial values we gave to K1 and K2 were 1, and that is between these bounds. So I'm just going to run these two bits. And then we're going to just link that into a random variable set, and then into an input. And then we're just going to create our model for Bayesian model updating. And this is going to be eigenvalues. So I'm just going to open up what this file looks like, what this file is. And it's basically exactly like eigenvalues perturb, but without this random noise added to the output. Okay, I'm just going to run that section. The next part we need is basically a likelihood function, which basically just gives you the probability of a point in the input space given the model and given our synthetic data. So basically just we'll run a point in our input space, evaluate it, and then compare it to the output data. So to construct this class, we basically need to give it our model, the calibration data, and this thing called a width factor basically governs the width of the probability distribution of the likelihood. This often needs to be tweaked, but for this example, it's 2, and this needs to be the dimensionality of the output. In this case, the output is 2-dimensional. We have a y1 and a y2. So let me just run that. Okay, And finally, we can construct a Bayesian model updating object where we give it the likelihood and just the output names. So the names that the output variables that we want to calibrate with respect to. This is a little bit confusing uh, because we're calibrating for the input. So what this process gives us is basically samples of the input. The output of this method is basically the inputs to the model. Just run that. And then basically, finally, we can run this apply to MCMC method, which will basically generate samples of K1 and K2. When running this, it's going to basically begin a parallel pool. So it's going to run this thing in parallel. So the first thing it's going to do is it's going to create a bunch of parallel copies of this method in your course. And so yes, just hello. Okay, and once the parallel pool is created, it will begin sampling. Bayesian model updating can be quite an expensive way of calibrating. It depends on how expensive it is for your model to run. I think this example for taking 600 samples, which is quite a lot of the input. It takes it takes approximately that long. And finally, this final part here is just for plotting the output. Okay, so this is basically samples of our calibrated input. So this is K1 over here, this is K2, and this is samples of their joint distribution. If you remember, we started off with values of 1, 1, which is captured here by the posterior, including some uncertainty about that point. But there's also a second point captured at 2 and 0.5, which is a second valid answer to this updating process. Both of these points basically produce the same output value. The good thing about Bayesian model updating is it can capture both of those answers. And finally, this is just a plot of our calibrated model versus the calibration data. So the orange points are basically the synthetic data we started with, and the blue points is basically each one of these points propagated out to the output space. Okay, well, that's it. Thank you for listening, and yeah, cheers.